Hi, with this video lecture, we are going to start your third chapter, which is crystallization, segregation, and casting of metals. And as a reminder, I would like to talk that in the previous chapter, we talk about the different kind of phase diagrams, and we especially learned about the phase diagram for iron carbon system. We have learned about eutectic, eutectoid, peritectic, the different kind of reactions. So at this point we are well aware of what is phase transitions and how the different phases forms during a phase transition. As well as I will like to remind you that from the liquid state, if we looked at a phase diagram from the liquid state, when we cool down the sample or slowly decrease the temperature, different reactions or transformation comes to play, and we get a different solid state, hence the crystallization comes to play. So So here in this chapter, we will talk broadly about the different aspects of crystallization, and I will like to introduce you, or I like to tell you that with the crystallization actually happens in two parts. First is nucleation, and other one is growth. So it starts with nucleation, and it forms a whole crystal or a complete crystalline structure by the growth of the nucleus. So in this slide, I will like to explain you what is nucleation. But we have already, if you remember, we have already talked about nucleation. I have given you a couple of examples of nucleation. So nucleation is again of two types, homogeneous and heterogeneous nucleation. I want to tell you here very clearly, when I say about the nucleation, that's at that point of time I'm trying to mean that the temperature of the whole system is continuously decreasing from the single phase liquid state, and and the temperature at the point when I am looking for, or I'm trying to see the nucleation, is must be less than the temperature at the liquid state. So here at the here let us talk about the homogeneous nucleation. Here you can see the nucleus has started forming at the core of the liquid, at the middle of the liquid. But if I look at the heterogeneous nucleation, you can see the nucleation has started at the borders or at the surface of the liquid. So that is the basic difference between homogeneous and heterogeneous nucleation. In one case, the nucleus starts growing at the core of the liquid, or in the other case, it starts growing at the surface or at the grain boundaries or at the sides of the at the different sides. So this is the basic difference between them. So here I will give you a systematic definition of nucleus, as well as what is homogeneous and what is heterogeneous nucleation. So as I have already discussed with you in the last chapter, that nucleation is actually is the appearance of very small particles or nuclei of new phases which are capable of growing. And here the for the homogeneous nucleation is the process in which nuclei are randomly and spontaneously grow irreversibly to form a new phase. On the other hand, heterogeneous nucleation occurs or starts occurring at the surface. So here let's talk about homogeneous nucleation. So as I said already, it always starts at the core of the liquid. Here if you see, this pink portion is my liquid and the orange portion is the solid side. And for example, we consider that the radius of this nucleated portion is r, and the volume is, hence the volume will be 4 by 3 pi r cube, and the area is 4 pi r square. So let's see what all the forces are working or in play when this nucleation starts happening. So here the equation 1 is a term that is the that is a sum of the surface free energy, and this is the second term is for surface free energy, and the first term is for volume free energy. So the total free energy of the system in case of this nucleation is a combination of volume free energy plus surface free energy. So this is nothing but the volume 4 by 3 pi r cube, where del GV is the free energy term. On the other hand, in the second term, 4 pi square is the surface area, and gamma is your free energy term. So when we plot these terms with respect to radius, let's see how it changes, or how the changes comes to play in this case. So here in the figure 1, you can see the blue line, which indicates the variation of volume free energy with radius is negative and decreases with the radius. On the other hand, if you see at the red line, which is designated for surface free energy, it increases with which is positive actually, and increases with the square term r in the equation. So the volume free energy decreases and surface free energy increases. Now let's see how the total free energy varies with the radius. Here in the second picture, you can see this green line is your total free energy, and as well as both the free energies for volume and surface are also plotted here. So here you can see this curve. First at the beginning it increases it increases up to the maximum, and then it finally decreases. Now when I see this graph, what is the physical meaning of this graph? Let's try to do that. So in physical sense, this means that as a solid particle begins to form, form as atoms in the liquid will cluster together, or I can see as the solid particle will start forming, the solid will cluster together and its free energy will first increase. So when the solid is trying to form, the free energy will first increase, and if the cluster of the solid reaches a certain size, that means which is designated by this radius, to a certain size, then it decreases. Here it's decreasing after a certain size, and this maximum radius is r star, which is your critical radius, and the maximum free energy is del G star, which is the critical free energy change. So on the other hand, it means that a cluster of radius, that means is a radius less than r star or critical radius, will shrink and dissolve in the subcritical particle. or the liquid. If a cluster have radius less than r star, it will dissolve in the liquid, and we will call it as it will shrink and dissolve in the liquid, and we'll call it as embryo. Whereas if a cluster have radius more than r star, it will it is termed as a nucleus, and it will tend to grow spontaneously. Now, why I have introduced the term spontaneously here? Because you must know that if for a system the free energy is negative, the processes tend to be spontaneous. Here you can see the free energy is decreasing, and finally it's negative. That means the process is spontaneous. So once the cluster reaches this radius r star and crosses this point, it is the nucleus is tend to grow spontaneously. And this term del G star, the critical free energy, is also can be called or corresponds to activation free energy, which is required for the formation of a stable nucleus. Equivalently, I can say that it's or I can consider it as the energy barrier to the nucleation process. So, as I have already discussed, that if if this energy barrier is crossed, which is del G star, the cluster or the nucleus is tend to be stable. But if it doesn't reach this point or this radius, the cluster tend to be unstable, and we call it as embryo. So let's move to the next slide. So here we are trying to find the equation 2. We are trying to find a equation or a terminology for the critical radius for the homogeneous nucleation system. Now you must be wondering how I got this term. So this term is obtained from the equation 1 that you can see here, and I have differentiated the equation 1 with respect to radius r, and then equating to 0. Highly advisable, please don't try to remember, rather try to derive this thing, and it's very easy to calculate. So if you do this operation, we will reach up to a point where I can calculate this critical radius, and critical radius is given by minus 2 gamma divided by del G V. So now if I put this term, the value for critical radius in the equation 1, I will get a formulation or a term for the activation free energy required for homogeneous nucleation, which is given by del G star, and which is equal to 16 pi gamma cube divided by 3 del G V square. So let's see how this free energy term depends on temperature, because when I'm talking about this phase diagram and the cooling process, of course the temperature is a very important quantity. So I'm trying to find a relation between the free energy of the homogeneous nucleus and nucleation and the temperature. So as we all know that we have a relation of free energy in terms of enthalpy or the latent heat of fusion. So from that equation we found this terminology, and I'm trying to write the del GV, the free energy of the volume in terms of temperature, which is given as del GF Tm minus T and by Tm. So here I want to make it clear for you that Tm is the temperature of solidification, and del HF is the latent heat of fusion. Now, if I put this value of del GV in equation 2, for the equation which stands for the critical radius, I will find an equation of critical radius in terms of temperature. And similarly, if I put the same values in the equation 3, I will find an equation of the equation of critical free energy in terms of temperature, which is my equation 6. So here we have tried to plot the values of G versus radius for different temperatures. So here you can see very clearly that we have two temperature ranges. One is T2 and another one is T1. And it's very clear that T2 is higher than T1. That means this temperature, the temperature T2 is more than the temperature T1. And here when we plot it, we found that for T1, which is a lower temperature, we have higher value of critical radius. But when the temperature, for the temperature T2 at lower temperature, the value of critical radius is less, as well as the value of the critical free energy for homogeneous nucleation is also less. So hence we can conclude that del G decreases as temperature decreases. That means the energy that needs to overcome for the homogeneous nucleation to come to play completely depends on the temperature. For lower temperature, we have to invest less energy for the homogeneous nucleation to take place. On the other hand, for a higher temperature, we have to invest more energy for the homogeneous nucleation to take place. And here the here the term n star so comes, and the n star means number of stable nuclei. So if you remember in the previous slides, I told you what is a stable nuclei. A stable nuclei means a cluster whose radius is more than r star. So once the cluster crosses or the radius of r star, we have termed this as we consider it as a stable nuclei, and below the radius r star it's still a embryo. So equation 7 stands for the n star, which is for number of stable nuclei, which is given by k1 exponential minus del G star by kt, where k is the Boltzmann constant, t is the temperature, and k1 is a constant. And this constant k1 stands for the total number of nuclei of the solid phase. So in the figure 1 or in the graph 1, you can see that that the number of stable nuclei is plotted against temperature, and you could see here as the temperature is lowered below Tm. Tm is the temperature of solidification. As the temperature is lower below Tm, the exponential term in the equation decreases. So the exponential term decreases when the temperature is below Tm, such that the magnitude n star increases. So here you can see we have a minus sign. So when when it will go negative. So overall, the magnitude of n star will increase. The temperature dependence is shown in this graph. So this is the explanation for graph 1. So here you can see that we have another term Vd, which is your equation 8. So Vd is the frequency of atomic attachment versus temperature. Here in this graph you can see very clearly that in this case the exponential term increases, the frequency increases, and finally this is your equation number 9, which is the nucleation rate expressed for homogeneous nucleation. So when I say nucleation rate, that means the nucleation with respect to the variation of nucleation with respect to time. So here you can see that the green graph, and the green graph is given by n star, which denotes the nucleation rate. And here there is one new term, that is K3. So K3 is the number of atoms on a surface, on a nucleus surface. So here you can see that lowering the temperature below Tm, the nucleation rate first increases and achieves maximum, and subsequently it diminishes. So it first increases and slowly decreases. And you can see this is del T is the cooling required for the whole process. So this is what is our conclusion about this homogeneous nucleation, that the rate of the homogeneous nucleation first increases and then it slowly decreases, and the and the del T is our required cooling. So let's move to the next and the other type of nucleation, which I call is as heterogeneous nucleation. So in the first sentence it's written very clearly or boldly that it is easier for nucleation to occur at a surface and interfaces than other sites. And going forward in the couple of few slides, we will see how and why it's easier for heterogeneous nucleation to occur rather than homogeneous nucleation. So to understand this phenomena, we have considered an interface, and I'm considering this is the liquid phase, and slowly the solid phase has started growing at the boundary. And when I consider the situation, a couple of different forces or interfacial forces will come to play. So here the first kind of force, I'm considering it as a solid surface force, which is given by gamma Si, and and here this is the gamma Si. The second type of force is solid liquid force, and solid liquid force is given by gamma Sl. And the third type is liquid surface force, which is given as gamma IL. And here theta is the wetting angle. So I'm considering that and in this situation we considered that both the liquid and solid phases wet the flat surface. So let's see how the overall tension force or surface tension force looks like. So equation 10 stands for the overall surface tension force, and which is given by gamma IL is equal to gamma SI plus gamma SL cos of theta. So going forward, we will try to calculate the critical radius and critical free energy in this case also, as we did in our previous case. So Here you can see the value of critical radius for a stable heterogeneous nucleation, which is given as R star equal to minus 2 gamma SL divided by del GV, and the activation free energy is required for formation of a stable nuclei. So here you can see a new term, which is S theta, and S theta will have numerical value from 0 to unity, and it stands for the shape of the nuclei. Because in last case we considered the nucleus to grow as a sphere, but here we see it's not a complete sphere, so this term S theta stands for the shape of the nucleus. So if you compare this R star for heterogeneous nucleation and homogeneous nucleation, you will see that it's exactly the same term, apart from this surface energy term stands for SL, and in it's the same, the value is absolutely same in both of the cases for the critical radius. And here you will see that the activation free energy term in case of heterogeneous and homogeneous system is same, but there is a difference of only S theta. So going forward, we will compare the critical radius and critical free energy of both of the system for homogeneous and heterogeneous nucleation. Okay, so here in this figure, this first figure, figure number 10.06, it's a schematic free energy versus embryo or nucleus radius plot on which are present curves for both homogeneous and heterogeneous nucleation. Here you can see the blue line, which stands for heterogeneous nucleation. The critical energy or the activation free energy is lower compared to the homogeneous nucleation, whereas the homogeneous nucleation, you can see it's a red line, and the critical free energy of homogeneous nucleation is quite higher, whereas on the other hand, the critical radius in both of the cases are same, as I have discussed in the previous slide. It's the same, but there is a difference of critical free energy. And here is explanation. You can see why it's here, why one is greater than the other one, because the del G star of heterogeneous is equal to del G star of homogeneous into S theta. So clearly this term is a stands for a lower critical free energy. So when the activation energy or critical free energy is lower, the phenomena is there is possibility of occurrence of the phenomena is higher. That means, and that's the reason it has been told in the first slide for the heterogeneous nucleation, that heterogeneous nucleation is more likely to occur because it requires less energy, but homogeneous nucleation is less likely to occur because it requires a lot of energy to overcome the criteria of critical radius. So let's see how the nucleation rate varies in case of heterogeneous and homogeneous nucleation. So here you can see for the blue line stands for the heterogeneous nucleation rate, and the red line stands for the homogeneous nucleation rate. And I have just plotted, and the nucleation rate is plotted with respect to temperature. So here it means that for this heterogeneous term, you can see the you can see that the cooling temperature is, or the temperature difference, that it needs a lot of cooling is high, whereas for heterogeneous nucleation the cooling temperature is comparatively low, and hence another reason why the heterogeneous nucleation is more likely to take place. So I'm closing this video lecture here. Thank you so much.